Hi there, my name is Marcel Flores. Today I'll be presenting Building Out the Basics with Hoplets. This is joint work with my colleague Prathy Raman from the Verizon media platform. One of the challenges in operating a content delivery network is understanding the paths between the CDN and its end users. These end users are sending requests to the CDN, who is then replying with content. But sometimes what happens is there are issues on the paths between the CDN and its users. Now, rarely these issues are hard disconnects where we actually lose connectivity with the clients, but much more frequently these are soft degradations in performance, that is to say increases in round trip time. These can be caused by routing changes that might result in circuitous paths, persistent congestion in mid-tier providers that result in regular queuing delays, or poor replica selection, where end users are connecting to faraway CDN replicas that might have to do things like cross an ocean to reach the end users. So what we'd like to do is we'd like to be able to identify these issues on these paths and improve them. Improving them might be something like adjusting our replica selection by modifying our Anycast announcements. That might mean adjusting our outbound routing or similar changes. But we have so many clients and there are so many potential degradations that this problem is often intractable. However, our trusty tool traceroute can help us out here. And what we can do is we can send traceroutes from the CDN to these end users. And when we look at these actual paths, we see that the underlying picture is a little bit different. In particular, these top two clients actually had a shared segment on their paths. The first two hops were the same. And that means if that degradation is actually occurring on that shared segment, addressing that problem could potentially improve performance for both of these end users. And likely this occurs all over the place, We have many clients who have shared paths that are experiencing these problems. So if we can focus on these, we can more efficiently improve performance at the CDN. So that's where Hoplets come in. Hoplets are an abstraction for describing common delay increases between providers and clients. And by identifying these common problems, we're able to most efficiently address performance challenges facing the CDN. So the way we're going to extract these is we're going to start with traceroutes. So we're going to have a traceroute between a source and a destination. In this case, our source will be the CDN, the destination, our end users. And we're going to represent each of the hops along that traceroute with these colored circles. And each color is going to represent a different autonomous system along that path. So what we're going to do is we're going to look at the inter-hop delays, that is to say the change in RTT between each of these hops. And what we're going to keep an eye out for are cases like this plus 50, where we see a sudden increase along the path. We note that 50 milliseconds is a pretty substantial increase given the relative size of this traceroute. So we're going to take the sudden increase in inter-hop RTTs and we're going to flag that for extraction. To actually do the extraction, what we'll do is we'll take either side of the link where we saw that increase and call that the center of the hoplet. We'll then take one AS prior and after the hoplet, giving us some context in the extracted entity. So that's what a hoplet is. It's just a subsequence of hops along a traceroute that demonstrated a sudden increase in inter-hop RTT. But to make these useful, we're going to need another piece of this puzzle. In particular, we're going to need a comparison function. So what we'll do is we'll introduce a comparison function that's based on the edit distance of the subsequence as a sequence of hops. So once we have that comparison function, given a collection of traceroutes, what we can do is we can extract hoplets. We can then perform hierarchical clustering on this large set of hoplets using this edit distance, grouping together hoplets that have low edit distance and likely represent the same underlying network structures. Once we have these clusters that we believe represent the same infrastructure underneath, we can answer questions about the frequency and magnitude of these RTT degradations that we see on that infrastructure. Now, of course, we are using traceroutes, and that means that there are a couple of caveats we have to be aware of. The traceroutes are only going to reveal the forward path, which means that there might be something happening on the reverse path that's actually causing these RTT increases. Indeed, past work has shown that this is often the case. Because we're also looking at the inter-hop times, we can't exactly locate where issue causes lie, Because they may be taking different return paths at each hop, they could be entirely different. But ultimately what we're going to use here is sort of a fatalistic approach. Basically, we're going to say that once we hit a hop that saw such an RTT increase, we know that we saw that increase, and whether or not those entities were responsible for that increase is immaterial. From the perspective of an operator, if we want to avoid paying that RTT penalty, we should avoid that hop. So with that in mind, we took a collection of traceroutes from the CDN towards end users. Over the course of about 24 hours, we took about 130,000 traceroutes to some of our top talkers. We generated the Hoplet set. We clustered them using the method described previously, and then we looked at what we saw. In particular, we're going to consider things on a regional basis to try and understand some of the underlying infrastructure. So the first thing we looked at is a regional breakdown of the mean Hoplet penalty in milliseconds. That is to say, how large the sudden increase in RTT penalty that we observed was in each of these Hoplets. The first thing to note is that Asia, Europe, and North America are largely clustered together, right? Even though they see a large range of penalties, they're relatively similar across the regions. South America, on the other hand, demonstrates an increase in penalty, right? At the median, we're looking at an almost 20 millisecond increase in mean penalty. What that tells us is that reaching to South American clients, we much more frequently encounter large penalties. We also wanted to take a look at some of the topological features visible in these Hoplets. To this end, we took the AS hegemony. So we asked ourselves, when we observe a Hoplet, how important is the AS where we observe that Hoplet to the destination network? And AS hegemony is a measure that answers exactly this question. So for each Hoplet, we looked at the AS hegemony and broke them down by regions again. And again, we see that South America stands out from the rest of the pack. That is to say, we see greater hegemony at the Hoplet centers for a larger fraction of Hoplets. Essentially, we're seeing that there are fewer publicly visible alternative paths available in the South American infrastructure, likely indicating something about the nature of the underlying deployments. So bringing it all together, Hoplets offer a mechanism for succinctly summarizing traceroutes to highlight common issues. Using the CDN, we were able to examine 130,000 traceroutes, where we were able to look at some of the regional performance breakdowns and some of the behaviors that we observe in each of these regions. We also noted that about 20% of Hoplets occur on paths with no clear alternative. That is to say, there's not any clever routing we could do to work around these hops. We also demonstrated that Hoplets are agnostic to source. Even though we did much of our experimentation in the context of the CDN, it will really work with any source of traceroutes. For example, RIPE Atlas, an analysis in which we were able to find a likely routing misconfiguration with one of the root letters. So that's all I have time for here today, but I'll now be happy to take any questions. Thanks so much.